Alright, so here we are for 8.4 rational functions. Our goal is mainly to graph rational functions and transform rational functions. There's a lot of, say, good formula notes that you need to keep track of, so make sure you have that ready for your note card and start working on your note card as soon as possible. Okay, so what is a rational function? A rational function is a function that can be written as a ratio of two polynomials. The parent function for a rational function is f of x is equal to 1 over x. So when we look at the graph of that would look something like this, where you have what is called a hyperbola. Okay, so this is a hyperbola, and you notice there's a break between them. Those breaks are actually like horizontal and vertical lines that you can find that are called asymptotes. There's a vertical asymptote and a horizontal asymptote. The horizontal asymptote is that for the parent is at y equals 0. The vertical one is at x equals 0. Okay, so those little red lines I drew, those broken lines, those are asymptotes. They're lines that the graph gets close to but does not reach. Okay, so you can kind of see the arrows are getting closer, 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 but they're not quite there. Okay, so let's look at a basic transformations. F of x is equal to a over x minus h plus k. So this is the one that's a little different than all the other ones we've seen. A is still the vertical stretch, and if I have a negative in front of there, it's still going to be a vertical stretch or compression, I should say. Negative would be a reflection. We'll talk about like bigger and smaller numbers, but we'll kind of go from there. H is a horizontal translation, and x equals h every time. In other words, if you say x, set this x minus h equals 0, take the opposite of this h, you will have the vertical asymptote. The k is your vertical translation, how much you moved up or down, and y equals k will become your horizontal asymptote. So keep that in mind, how those form. So let's give an example that covers all that. So I want you to graph 1 over x minus 3 minus 5. Now, what I would do, if I'm graphing this by hand, I would first figure out my vertical and horizontal asymptotes. So here my vertical asymptote is x equals 3, taking the opposite of that x minus 3, or setting that x minus 3 equal to 0. The horizontal asymptote is that k, which is a negative 5, so y is equal to negative 5. So I can draw my asymptotes. And once I've drawn my asymptotes, basically I know I have a graph that should be those hyperbolas kind of heading towards that center point right here. Okay, so you can see how I've done that, and there you go. That's it. That's just a rough graph. It doesn't have to be perfect. I'm not going to worry about getting the exact points, but you get the idea. Obviously, if I asked you on a multiple choice test which one would be the correct one, you could graph it on your calculator and kind of see and compare. But it helps to know where those asymptotes are. Okay, so let's look at another example. Graph the f of x is equal to negative 1 over x plus 1. Okay, vertical asymptote would be x equals negative 1. Horizontal asymptote, there is no k, so my horizontal asymptote in this case will have to be 0, because I'm saying like plus 0. For these basic ones, you have to have a horizontal asymptote. And the negative 1, because it's a negative a, means a reflection. So that means I flip-flop them. Notice they're in like the other quadrants, the blank ones from last time. And there you go. That's some basic transformations, and you can figure out what they are. It's very simple. If you have any questions, feel free to ask. Now, we need to, before we move on, talk about what's a continuous function and discontinuous functions. A continuous function is a function with no gaps or breaks. Linear, quadratic, all the other ones we've done before were continuous. With rational functions, we create what are called discontinuous functions, functions with gaps or breaks. And so we need to make sure we find all those gaps or breaks. So there's a lot to cover here. With rational functions, when you want to graph them, if they're not in the other format, which was like the transformation format, we'll call it like that, we need to make sure that we factor the numerator and denominator. There will be a hole if any factors cancel. Leftover factors in the denominator indicate a vertical asymptote. So keep in mind there's possibilities to have more than one vertical asymptote. Zeros are determined by any remaining numerator factors. Okay, those are where they cross the x-axis. So make sure you've got all this. This is something to kind of keep in mind and keep on your note card. Then there's something special for horizontal asymptotes. There's actually 3 possibilities for horizontal asymptotes, and so you need to make sure you have this on a note card. This is not something that's easy to remember. If the degree of the numerator, this is before you're factoring, if the degree of the numerator is larger than the degree of the denominator, you have no horizontal asymptote. If the numerator degree is if the degree of the numerator is smaller than the degree of the denominator, your horizontal asymptote is y equals 0. If the degree of the numerator equals the degree of the denominator, your horizontal asymptote is the leading coefficient of the numerator over the leading coefficient of the denominator. It's really not that difficult. It comes down to 3 cases. Either you have no horizontal asymptote, it's y equals 0, or it's the leading coefficients. But you just got to make sure you have this. And this kind of keeps it very simple. Okay, so for example, here's how this would all come together. Okay, so here we have f of x is equal to x squared minus x minus 2 over x squared minus 4. Okay, I'll go ahead and factor this, but keep in mind I'll come back and look at this, the original way it's written first, or in a minute. So when I factor this, again, minus minus is plus minus, and when I say x squared minus a number, it's automatically plus and minus. 1 and 2, multiply to give me a 2, take the square root of 4 and I get 2. Okay, so those are factoring rules that you should remember. Now, horizontal asymptotes. Since the degrees are equal, it's x squared on top, x squared on the bottom. That means it's automatically the leading coefficients, which in this case is 1 and 1. So y is equal to 1. So that's where my horizontal asymptote is located. Then if I want to find any holes, holes are where the factors that cancel out. X minus 2 canceled out. So if you set that equal to 0, x minus 2 equal to 0 would mean x is equal to 2. Then the vertical asymptotes. Looking at the leftover denominator, and I would have the x plus 2 set equal to 0, it would give me x minus 2. Zeros, where it crosses the x-axis. Set the numerator factor that's left over into to set it equal to 0, and that would tell me the zeros are located at x equals negative 1. So this is something, again, coming back to factoring, that if you can do the factoring, should make it really easy. Okay, so here's another one. There's the original equation, x squared plus 3x plus 2 over 2x plus 2, and then I've already shown you how it looks factored. Remember, plus plus is plus plus, 1 times 2 is 2, 1 plus 2 is 3. 2x plus 2, I have x plus 1 and a 2 on the outside because I can factor out the 2. So now I factor this, and I'm going to go ahead and say the horizontal asymptote, there isn't one, because why? The x squared is greater than the x1. The degree of the numerator is greater than the degree of the denominator. So there is no horizontal asymptote. Holes. X plus 1's cancel out, so the opposite of that is x equals negative 1. Vertical asymptotes. There are none, because there's no x factor left. 0 would be at x equals negative 2, because the numerator had a factor left over of 2, or x plus 2. So again, not something that should be very difficult. Okay, here's my last example. F of x is equal to x minus 2 over x squared plus x. And then you can see there the factored form. I factored out the x and left me with x times x plus 1 on the denominator. So we look at this horizontal asymptote. The numerator is smaller than the denominator degree, so that means it's automatically y equals 0. Okay, then I look at the holes. There are no common factors, so there are no holes. What that means is, if you look at the graph, if you have a hole, it's like it skips a space, a very small space, and you probably won't even see it on the calculator, but that's what we mean by hole. Vertical asymptotes. The vertical asymptotes are, well, x. There's actually 2 here. because this factor is x equals 0, and then the other factor is x equals -1. So that means there's actually going to be two vertical asymptotes, one at 0 and one at -1. So you kind of see something little, maybe trapped rational function. And then finally the 0 is at x is equal to 2. Okay. So that's, again, like I said, that's the graphing rational functions in a nutshell. If you do have any questions, feel free to send it to me through Edmodo.